Hello, and welcome back to Turing Complete. We are maybe on the last leg, at least in terms of playing session, not in terms of VOD. We have 3 more sections to go. So, previously, we reached a point of a working computer, and then we pushed on further. Yeah, we have 3 more to go. I assume, based on how this level looks, there's gonna be more past it, which I might revisit once the game is out completely. But we'll have to see. Yeah, so let's get back to doing more computer stuff. Now that we know we're not going to get eaten, and well, we got the basics of a computer working, it makes sense to go further. Using the instruction of your computer, read the inputs twice and XOR the 2 values together. Ah! So we're gonna be doing this in assembly is what I'm guessing they mean. Right, because we didn't implement XOR, did we? Uh-huh. So we'll have to do it this way then. Okay. What makes sense is drawing out the circuit first using pen and paper, or in my case, digital tablet and notepad. So let me plug that in first. Let me get you out of the way. There we go. Now, excuse me as I forget what exactly are the... Let me just... Okay. Let me first open up Notepad. Zoop. Okay, now. The one thing I forget is which one is an OR and which one's an AND. Okay, the OR are the pointy ones, the AND are the round ones. Okay. So, what we want is an XOR. I don't remember. Wait, what does an XOR look like again? It looks okay. It's pointy with a tip at the end. Okay. Yeah, I don't remember shapes. So this is an XOR. Okay, and what is this equivalent to? So this would be equivalent to, I think... Okay, if we just do the 1-bit version, because then the 8-bit version just translates. The 1-bit version, we either check... So it takes in 2 inputs. If I remember correctly. It takes in 2 inputs, returns 1. So, what we can do is we can connect the first one to here, second one there, and what we're going to do is we're going to check, we're going to not one of these, like that, and then I think we're going to end them. So this will be true exactly when the top one is false and the bottom one is true, and then we do the exact same thing. And then we just do an OR on the last two. Okay. So this is an AND. Maybe I should do capital. And this is an OR. Not. Okay, so this is a circuit we're building. Although... No, we'll just do that. Okay. So, what makes sense is, since we have six, well, yeah, we have 6 buffers, probably makes sense to stick our 2 numbers into, I guess, into 1 and 2. Put it, and then we store the actual numbers into 4 and 5. Then we ORed them. Okay. So let's do that. Maybe I should have a notepad scene so I don't have to show my entire screen to everyone every time I use a notepad. That would take too much work though. So, let's see if I'm not the component factory. Oh gosh. Yeah, I spent 1 day not playing this game and then I forgot how to play it. Okay. So, we need to start with input. So into 1 and into 2 is gonna send the inputs to input 1 and input 2, which is exactly what we want. Copy is... I don't remember what copy is. I think this is copy. From input to register 1 and then to register 2. Alright, how badly... Oh, whoops. Okay. How badly did I mess up? Yeah, I got it reversed. Okay. So now we can go into 1, into 2. So we've read in twice, and now we need to do the operations. So we're gonna first do a not. So not 1. We need a not 1, so we need to compute. Not 1. Oh yeah, we need... Wait, do we actually have a not operation? We don't, do we? It just occurred to me, we don't actually have a not operation, I think. We have OR, we have NAND, and NOR, add, and sub. Oh, okay, we actually have to... do it ourselves. Oh, that's fine. We can do it. We can do it. We can do it. It'll just be more annoying. Okay, so instead of going 1, 2, we should go 4, 5. Wait, but I don't... Then we run out of space. Pain. Because the issue, so I have to think, do we have a way of getting not in? Because that's what we need right now. We need the ability to do not. Or, wait. It's not subtraction. I don't think we can use subtraction, actually. Could we use subtraction instead of not? No, I don't think so, because it's basically pairwise. No, we can't use subtraction. Hang on. So, let me come back out. Show. So, the issue is this strategy is we don't actually have access to a NOT gate. These ones. Which is only slightly problematic because it means that we would have to we can still make a NOT or use NOT in the context of the program by using a NAND gate or NOR gate. That would effectively work like a NOT, but it's more annoying and more fiddly. So instead, what we'll use is the kind of NAND-centered way of doing it, which is, I think I demonstrated it earlier, and as an example. I think what you can do is you can do this. Oh, not like that. Have a second NAND. I should be writing them capital. This might work better, because now I don't actually use a NOT. I don't know if it is better actually. And I would also have to verify the correctness of this quickly. 0 0, so that goes to 1. 0 1 0 1, that goes to 1 1, that goes to 0. Okay, that's correct. 0 1, that goes to 1, that goes to 0, that goes to 1. Yeah, so, and then 1 1, the center goes to 0, those go to 1. Yeah, so if the two inputs are the same, so if the two inputs are 1, then that goes, this center bit goes to 0, which means both of these go to 1, which means that this goes to 0. If both of these are 0, this goes to 1s. Yeah, so if both of these are 0, then both of these will be 1, and this goes to 1. If it's 1 and 0, 1 0, the bottom one goes to 1. This one goes to 1, so it's 1 1, so that goes to 0, so that goes to 1, and the same. Okay, so this is equivalent to an XOR. The question is this easy to compute? How many intermediary solutions do we, intermediary values? Because we would have to calculate, I guess we would first calculate the NAND of the first two, of the initial two values. We will have to save it, Then we would have to NAND that value that we get together, and together. No, yeah, actually, that's very doable. So we're just gonna use this circuit, basically. The bottom one. It'll be a lot easier. So, we are going to do... we're going to send these into the the fourth and fifth registry. So the fourth registry. So actually into 4. We delete that one and then into 5. So we'll do the fourth and fifth registry instead. We then need to 5 to 1. Oh, we can do 4 to 1 actually. 4 to 1. So copy. So 4 to 1. Then we need a 5 to 2. So that is 5 to 2. And then we need a NAND. We need a NAND. NAND is this, and I think these two, if I remember correctly. Oh, I got them mixed up again. Oh, NAND is just the right one. And I clicked out again. Okay. So we have 4 to 1. All right. Oh. We need into 4, into 5. Am I on the right scene? I'm on the wrong scene. There we go. 5 to 2. And then we do a NAND. So this will get the... So we now have the inputs. So NAND of inputs. That's what we currently have here. And so now we want 3 to 2, I think. So that is copy number 3 to number 2. 3 to 2. So from this point on, yeah, the so right now the NAND of the two inputs is in 2, and now we're gonna drag the first input to 1. So we call it X. So now we NAND of X with first input. And now we're gonna drag that output to 4. We don't need the output anymore. So we'll just drag the 3 to 4. It's 3 to 4. And now we need 5 to 1. So 5 to 1. Well, that is correct. Oh my goodness, I am mixing all of these up. Let me just double check. Compute is this, copy is this. We need to be certain. Let me just close this. Okay. Just using a mixture of all these. Into is correct. Okay, NAND is correct. There we go. Now they're all correct. That's 5 to 2. Okay. So now we'll drag 3 to 4. And now we do 5 to 1. So now the second input is there, and now we NAND of X with second input. And now we drag 4 to 2. So now we don't need X anymore. We can discard X. Now we're gonna drag our output of 3 to 1. Or actually, let's just reuse 3 to 2. And so now we just need 4 to 1. Yeah, so now it's just 3 to 2, 4 to 1, and then we NAND. Okay. Final NAND, and then out 3 is our last function. Out 3, which is just going to be register 3 to output. There we go. And this should work. Except it doesn't. Okay, where have I gone wrong? Okay, so 4 and 5 has the two numbers. 164 and 73. Let me just double check. What is... Because I could be wrong. This circuit should work. 164. I just wrote 7. Is 128. So yes, let me just write 128 plus 32 plus 4. So that would be 1 0 1 0 0 1 0 0. And 72 is the other number? 73 is the other number. 73 is equal to 64 plus 8 plus 1. So that is 0 1 0 0 1 0 0 1. So the output should be 1 1 1 0 1 1 0 1. Okay, what output are we getting? And then will give us 255, yes. So that 255 is in the center. Wait, what? Get back. $19.1. Why is it 163 all of a sudden? Ah. I will explain it. Something else happened. Okay. 255, yeah. So 91. That got to 4. Now we need 5 to 1. 5 to 1 is wrong as well. Where are they over? Okay, now they're all right. The game crashed. Fancy! Give me a moment, I have to resize it now. Okay. Did this get saved? Hopefully it did. There we go. Okay. My logic is sound. Perfect. We got it. Don't know why it took me that long. Create a circuit that always outputs a number 164. What an oddly specific number. But sure. This will be an easy one. In fact, let's get it as close as possible. Oh wait, yeah, we want the other one. Okay, on. And off. We want 164. That's 128 plus 32 plus 4. Everything else, we don't need to do this, but for the sake of completion. Done. Create a circuit that XORs 2 bytes bitwise. So as I said, we'll use the fancy ass circuit that I wrote down. But I mean, there's many ways of doing it. There we go. Output, output this when both inputs are the same. Okay. So basically what we're doing is we are going to take... Wait, we don't have an XOR. Oh man. I thought we were gonna get access to one, because that would be easy. Because then we just XOR them and check if it's 0. Sure. That should be neat. There's probably another way of doing it. I actually didn't see this thing before. That would be useful. Oh wait, we can subtract. We can just take the difference between the two and check if it's equal to 0. Wait, how do we check if it's equal to 0? You know what? It's probably easier if we just do it this way. No, it's not easier. No, we should do it we should definitely do it this way. I mean, this is not the way a computer would implement this, because this is not exactly the most efficient way. But who said anything about being efficient? We will break this bit apart, and we're going to OR everything. We're gonna check for 0. I'm surprised I actually don't have something that just checks for 0. That's okay. We'll do it over here. And then the final bit, just to be extra fancy, we'll use a NOR. So that we don't have to add an extra not. But this is just simply this. We're basically ORing everything. We check to see if any of the values is 1. And if any of the values is 1, we output 0. That's all we're doing. Because if any of the output is 1, this final thing will be 0. Look at that. And we're done. And because what we're basically doing is taking the difference between two numbers, this number will precisely be 0. If the two numbers are equal, of course. Create a circuit that outputs true when the first input is less than the second. Interpret the byte as being unsigned. Okay. There are several ways of doing this. I think we can do this using the math operation, though. Again. Or maybe not, actually. Or actually, you know what? Maybe we actually can. Because the thing is... Do we have access to a NAND gate? Logical NAND gate. Yes, we do. No, I think this is not clean. I think we should just do it this way. Or do we actually want to subtract each other? Maybe we should. It actually could be useful to do it that way. Because then we only have to deal with one number and figure out its properties. That's a nice thing about using this, for instance. Let me just... If we do it this way, this means we only have to analyze the output of one number instead of if we did it the other way, which would be to break down two different 8-bit integers and try to formulate a property of these two. Doing it this way is easier, I think. Now, as I said, they are equivalent to some degree, but I feel like... Hang on, I have to think about if we can draw the same properties. Maybe we actually can't do it this way. Maybe we actually do have to break it down properly. Yeah, actually we have to break it down. This is unfortunate, but... Okay, let's just do it. Let's just break it down. No fun, fancy way. Or if there is, I can't think of it now. Determine if the... So it's true if only if the first input is strictly greater? Or strictly less? Hang on. What's the... When the first input is less than the second. So the way to do this is pairwise comparison. We basically output true if and only if the first bit is so if this is true, this is false, or if they're both equal, and then this is true and this is false, or if they're both equal, this is true, this is false, or they're both equal, so on and so forth. What does that look like in practice? It will look like, so we'll do an AND. And I think we use the 3-pin ends, basically. Or do we? Maybe we do. Or do we use a switch? Okay. So the first case, we want this to be false. And this to be true. I really don't want to do it this way, to be honest. This feels like it's going to be like a painful way of doing it, but... Okay, whatever. So this will be... So okay, well, wait, we have to run it via an OR gate, actually. Okay. Or they're equal. So we have these are equal. Actually, that would be an XOR gate. XNOR gate. So this is true if and only if they're equal. And... oh, you know what, actually? We're basically building... okay, there is a trick. I was thinking there is a trick to this, and there is one. We're basically going to build this circuit. Actually, let me explain the trick, because it does actually help. The idea is that we're going to build this circuit. Actually, I built part of it. We're going to do a NOT like this. So we're going to check to see either if this input is true or this is false. So this is the AND. Or what we're going to do is we're going to check to see if they're equal. That's the XOR. Oops. And then we're going to AND it with the next input. So we're going to do this. XOR. So or they're true, and then we'll carry it down 1, basically. Do this thing. So we'll do an AND here. Wait, hang on. These should be these should be these ones. We repeat the circuit, basically. So this would be a NOT like this. This would be an AND. Okay. And then what we do is we then basically repeat the same structure. So we put another XOR down there, and then we put a bunch of ANDs. And I think the way we shortcut this is we can actually build all 8 of these circuits for each of these inputs in one go if we just use the 8-bit version. So what I mean is, we'll take the AND and we'll negate it. We'll also AND the negation. And that basically shortcuts that will allow us to shortcut a lot of the calculations for... Actually, we can't do this. It allows us to shortcut a lot of like the building of the gates. Because now all we need to do is, I think... So we still need to break it down, by the way. But we can now break it down in a different way. So now we need to XOR these two. And now using these two numbers, we can basically calculate the thing we need to do. So actually, I'll give myself a little bit of extra space. Zoop. This part we have to do, I think, manually, but it'll be fine. So what we now need to do is basically these pins will light up if the corresponding bit is off in the top input and on in the bottom input. And we want to grab the earliest time when... Oh, actually, we need the XOR gate. Actually, we can do it afterwards. Maybe we don't need it. We want to grab the earliest time when this is false, basically. We want to find the earliest bit when this is false, which means that that's the first time there's a difference. And then we want to get the truth. So the question is, how do we do that part? Well, so I think what we can do is we can build it recursively, kind of. So I think that's the way we have to do it. Or is there a way of doing it? Maybe. I think that's the only way to do it. So if this is false, then we want this to be true. Okay. While my mind figures out the top part, the bottom part is actually quite simple. We'll just build a bunch of these switch gates. And then we want exactly one of these to be on. And the one that we want to be on will be dictated by the top circuit. Five, 6, 7. And then we connect all of these to the output. I, for some reason, grabbed the wrong switch. Okay. There we go. And now all we need to do is connect these ones properly. So, if this is off, we can use more switches actually. What we can do... Okay, I think I'm going to use it next door. So we will negate it afterwards. No, that would be negative. We want to negate it with a not. Okay. If this is on, okay, if this is on, we'll connect it to this one. Easy enough. If it's off, so that's when we'll run a not. And wait, that's the wrong not. Then we'll run a not here. So this will be, when this is off, this will be on. And then this one we want to be on. So this will be an AND here. Or both of these are off. So if this is off, then this is on. And so we want to connect this. Actually, that's a 1-bit decoder. What we want is a 1-bit decoder. Hang on. I think we can simplify this with a 1-bit decoder. Okay, and then this item will connect to the next one. So I think we end this. So if both of these are on, then this will be turned on. Otherwise, we need to OR it. Wait, is what we want a 1-bit decoder? Maybe not. I don't know why I'm... Okay. There's probably an easy trick to all of this, and I'm just blanking. It's off, so I think we want this at the very end. We want to run a 1-bit decoder first. If this one is on, that's when we connect it. And if this is off, we'll OR this and connect it to the next one. Okay, I think that's it. We'll OR these two values, and then we'll repeat this circuit. Oh, that will get messy. Hang on. Is there a way of doing this sensibly? I don't think so, because we don't have access to like a multiplication by 2 system. Wait, we do actually. We have oh, we don't have components in this level. That was also the wrong one. We want an OR. Yeah, and then we're gonna combine these two together, basically. Is the idea. Hang on, let's do this in the cleanest way possible. Oh, without... Alright. So let's clean this up. So what we're going to do, deck, and we are going to, we might actually have to move the entire thing back by 1, except that's not how you select a bunch of stuff. There we go. Okay, and then we'll move this guy all the way to the end. Soup. Okay. So we will do, so it will be a deck, and then for the deck, the first deck will just be very simple. We connect like this. For future ones, we have to end it first with the next symbol, however far away we might do it. So we'll OR. We will first thing we'll do is we'll deck. And then we will, with the bottom one, if these two are true, we'll connect it. Otherwise, with the top, we'll OR that one. Okay, hang on, we might need extra space. Just one extra, like that. And then we will we'll combine it like this. With an OR, like that. And then we'll repeat this structure as many times as we need to do it. So we'll... Can we just copy and paste, by the way? We can! Should we line it? Let's not line it up perfectly. I think we should specifically like... Oh, we ran out of space. No, I really don't like this solution. I feel like there has to be an easier way. And I just have to figure it out. Because I really don't like the solution. There's gotta be an easy way. There has to be an easy way. I refuse to do it. You know, I'm gonna refuse to do it the hard way unless I figure out an easy way of doing it. Because it's generally one I haven't really thought about. You know, we could actually build a multiplication by 2. It wouldn't be that hard. Do I need one, though? Okay, let me clear up the circuit. Maybe all this will come to bite me in the ass, and I'll have to do it the hard way. But give me some time to think. Because the solution I had in mind works. The circuit I was building works, but it's painful to logic with. I feel like there has to be a solution that uses the add symbol. I just have to figure out how to use it properly. So wait, actually I have an idea. No. So, what we have right now we have 2 bits, 2-bit integers, and normally the way you would compare is you would subtract 1. Okay, so we're checking, in this case we're checking if the first one's less than the second one. So maybe we should do, I mean, it doesn't really matter the way we do it. But if we take A, B as inputs, this is on the right scene, right? Yeah, it's on the right scene. If we take A, B as inputs, we want to check if B minus A is positive or negative. We can easily do that. The point is to get to that point. The only issue with this approach is right now we're dealing with unsigned. So what we need to do is to figure out a way of converting this problem so that we can deal with the unsigned version. Because then our problem becomes easier. Now we could actually, there's an easy thing, an easy kind of test we can actually do, which I just realized. We can test to see if a number, wait, why did I write like that? We can test if a number is at least 128 by just checking, or yes, by just checking if the last digit is 128, if the last bit is on. So if the 128 bit is on, like that means the number is greater than 128. So can we convert this to a test that tests if our number is negative? That has to be a way through. Using the fact that we can easily test if a number is bigger than 128. I think maybe an approach. No, that approach doesn't quite work. Well, we can definitely start with a simple test. The simple test is, oh, actually this could work. I think I have an idea. First, we test if the second number is above 128 and the first number is below 128. If we do that, easy, we return true. So if A is strictly less than 128 is greater than B. So in this case, easy true. Now, if it's false, that means either both A and B are less than 128, or both A and B are both 128, are greater than 128. In the first case, we'll add enough to A and B to make one of them 128. I think we should make, let's just make A 128 in both cases. And we can do that in a way that does not cause B to overflow, so that we can do this checking in one go. And the same here. We take away enough to make this number, to make both of these numbers, to make one of these numbers 128, and then the other number is some number. And then we can use the test to see if it's greater or less than 128 in order to figure out which number is bigger. And we can do that without dealing with individual bits. And the way we test to see if a number, well, the way we test is by checking if the last bit is on or off. To test if, not to test, to do this operation, to add enough to make it 128, we need to first find 128 minus a, and then we add it to both a and b. So we add that to a, that will give us a 128, and we'll add that to b. And that'll give us a number greater than 128. Okay, I think we have a solution. Yes. So, this is our solution. Oh wait, actually, wait, there's actually a reason why the add has a carry symbol. Maybe we don't even have to do this complicated thing. Wait. It might just be that if we subtract the two numbers... Yeah, I forgot about the carry. I was just thinking about wrapping around, but actually we can evaluate when the number wraps around. You know what? Yeah, actually that's a much simpler solution. Okay. Let me rewrite this. Okay, I figured it out. I think I figured it out. So, when we write a and minus b, those are both going to be numbers. Now, how we get from negative numbers to positive numbers is by overflowing. So that means that we go from a like 1 1 1 1 1 1 1 1 plus 1, we get to 0 0 0 0 0 0 0 0 0. So if we add 1 to this number, we go back to 0. Now, what I forgot before was this add bit actually tells us when we overflow. So if this happens, it'll actually output another bit. And one way we could test to see if a number is positive or negative is if we take a negative number and we overflow it. So if we take a negative number and we try to add more to it, if we don't overflow, that means that there isn't, A is not big enough to increment B to the point of overflowing. In other words, how do we say this? It would be A minus B is less than 0. So if the carry bit is off, that means A minus B is less than 0. Now this assumes that our numbers are less than 128. So we'll have to, I think we'll still have to do the testing to see if one bit is bigger than 128 and one isn't. But I think assuming that that we've done that, we can actually then use the carry bit in order to test to see if our number is in fact greater and less than 0. That way. Actually, it could also work without the carry bit? No, I don't think it can. Or maybe it can. Hang on. Maybe we specifically do b minus a. If we do b minus a, then I suddenly lost my train of thought here. Yeah, it's either a minus b or b minus b. Maybe they both work. Yeah. If we take its negation and we add them together, or maybe not even negation. Maybe we can use a not actually. Maybe a not works better. Okay. You know what? I think a not actually might work better. In fact, I think I have an idea. I have an idea. Okay. Take a number A. Yeah, this is such an interesting problem. If we take a number A. It's unsigned. This time it's unsigned. So A is an unsigned bit. What A means is that we've added a 1 to 0 8 times in order to get to A. So yeah, so we do 1 plus 1 plus 1 8 times. Now what is not A? I don't know. Not... Okay, we write not A like this. Now, I think, and I have to double check this, not A has the property that if we add plus 1 8 times, we end up overflowing. Actually, no. We actually end up directly at 255. No, my bad. And the way we can check this is true is by, well, a mathematical proof structure called induction. We check it's true for 0. Certainly it's true for 0. 0 plus 0 times 1 is in fact 0. And then the not of 0 is in fact 255. And then what we do is we consider, well, if we consider 1, well, the inverse would be 254? Yes. And then plus 1 is 255. So what we need... Okay, I think I am not... I've disconnected. Yeah, sorry, I've disconnected temporarily. So the point is, yes, a number plus its negation is 255. So if we add one more, we overflow it. But more importantly, if we add a number less than a to it, that will not overflow. But if we add a number bigger than a, it will overflow because of the overflowing thing. Okay, I think we figured it out. So all we need to do is we take our add, we will add one of them that's not. Hang on, we'll add it back to game. Okay. This is like 2 hours in. Well, not 2 hours in, but like an hour in. We'll take our add, we'll take our not. And yeah, we'll connect this way. So, and I think what we also need is we need to add one more. There we go. Oh no, we want strict equality. Okay. Got it. This circuit will work. Because right now we flipped and. We flipped the first one. So now it's a number where you need to add exactly the top number to reach 255. Now if the bottom number is the top number or less than the top number, then adding will not overflow the number, and so we will return false. But if the lower number is bigger than the top number, we will add more than enough to overflow 255, ergo causing this bit to overflow, and so this bit will come true. So for example, 28, there we go, it works. And if we put 32, it doesn't work. Okay, we figured it out. Oh gosh. This was, I think I definitely spent way too long on this problem, considering I had all the tools available at me. Whoops. I might actually break it down slightly differently when I upload it as a VOD. Create a circuit that outputs true when the first input is less than the second. Interpret the bytes as being signed. Wait, isn't that... Did I just click on the same... Oh, the signed version. Aha. Okay, this one's easier. I think. Is it easier? Okay, well, once again, I think we can probably get away with just using AND. Okay, this is the signed version. So we're using, okay, flip the signed. I think we're gonna use the overflow fact again. But I think we have to be slightly careful here. I think what we're doing here is we're taking the negation of this one, we're negating it, we're adding these two together, and now we're outputting the last bit. No, the other way around. We're negating the second input. So now this is the bottom minus top. If the bottom is bigger, this might actually, there's an edge case that might not cause this to work, which is specifically when it's minus 128. The issue is minus 128 negated gets us to 128, which is equivalent to minus 128. Yeah, minus 128 is an edge case that doesn't quite work with this system. But the idea is, this will work for almost every input. We might have to make a small exception. Yeah. 33. 109. Yeah, okay, it does work. So what we're doing is we're taking the bottom number, negating it, and adding it to the top number. If the result is positive, we're done. If otherwise, if it's negative, if the number is positive, we output it. If the number is negative, we output false. Actually, this system doesn't work because overflowing is also an issue that we have to take into account. We might have to. Hang on. Actually, let me think about why doesn't the original system work? Because it would treat 255 as being less than 1. As being greater than 1. So minus 1 would be greater than 1. That's the issue. This system almost works. It's just the edge cases that will ruin us if we do it this way. Yeah, for instance, if a number... Wait, if we have 1 and we have minus 1, this should output true. No, it should output false. Or, wait, what example would it be? It would be 1 and... I guess, yeah, minus 128 would be the example. Or even 127. Minus 127, that would become 127. So, if it's 1 and minus 127, we want the answer to be false. However, if we do it this way, 1 plus minus 127 minus 127 would become 128, which would become minus 128, which would output true. So that doesn't work. Yeah, so my idea didn't work. We need to do it a different way. Do we have to test the edge cases first, maybe? Is that the answer we need to do? If we first test if a number is greater than 0 and the other one's less than 0. Because that would be easy. Would it be easy? Maybe. It would just require, I think, like yeah, an XOR would basically tell us whether or not we should do it. Or kind of, actually we should break into bits, but maybe we don't want to break into bits quite yet. I'm sure there is a way of doing it using overflow. I'm just being silly right now. So if we... What if we somehow added 128 to both of them? Converted it to the 255 case and then just like did that. Would that work? That could actually work. Convert it to the unsigned version and then just use the add symbol, because then it will just be easy. We just do it the same way. You know what? That could actually work. Wait, that could be silly enough to work. Adding 128 is just a matter of flipping the final bit. Wait, actually, that could be dumb enough to work. So, we're just going to... No, we want the other one. So this is just the number 128. And we're gonna flip the final bit by just using XOR. And we need the... And if we do it this way, this is now the unsigned version of this problem, which we already have a solution for. This is equivalent to just adding 128. So then we need to not the top input. Was it the top input or the bottom? I don't remember. I think it was the bottom. Oh, and we don't want this. Okay, there we go. So this is the same construction. We're just adding 128 to both of them using an XOR. And it should work. Okay. We did it. Create a device that saves the program output on even ticks and outputs both bits on odd ticks. Wait, I didn't get it. Create a device that saves the program on the program output on even ticks and outputs both bits. Wait, hang on, I actually don't get it. Oh, is it like, okay, maybe I get it. No, not this. I think what they mean is make it the layer that duplicates values or something like that. Maybe. Or not duplicates, but it sends both bits. So this will be connected like this. We want not a max. I guess we kind of want a delay line and a decoder. A 1-bit decoder. This one will... here. We're connecting this guy to itself. So now it'll keep bigging it, switching these two around. Okay, so I think we want this to save first. No, that's the load. Like this. And then I think we want 2 switches as well. Oh no, we can leave this here. We just need 1 switch. Just the 1 switch. So we just connect this to this, and we only want this on when we are doing the loading, which is when this is on. So I think this works. Oh, I think we need a counter as well. Like this. Yeah, there we go. There we go. Finally, it's time for you to start building the leg architecture. The leg architecture is a computer that takes 4 bytes per tick from the program. The first byte describes the operation, called the opcode. Since many operations take 2 arguments, like add, or, etc., the second and third byte are for arguments. And since most operations return 1 result, the 4th byte is for the result. So what are we doing? So opcode sends the instruction, I guess. These 2 bits sends an argument, and then this sends a result and a result address. Okay, the following are the setup steps that need to be done in order to complete this level. Click on the schematic icon and create a new empty architecture. Place a program block with 4 outputs. Place a counter, set its increment to 4 and connect it to the program block. Add 6 registers. Click Edit Link Component on the program component and connect registers 0 to 5. Connect the counter to 6 and the output to 7. Finally, in this level, the opcode is always 0. This means we add arguments 1 and argument 2 and save the result to the destination. The value of an argument or destination refers to one of these places. Bonk. In the next level, you will implement more opcodes, which will require a different ALU than that of Overture. Okay, so first we need to make a new schematic. Leg. Okay, there's leg. Guess we'll edit it. Okay, we just copied it. Okay, there we go. That's the input and output. Okay. Alright. Let me closely follow this level log, because there's a lot to do. Program. So I guess we need to program. Bonk. Okay, so we have our 4 bits. Wait, so this will always trigger all 4. Wait. Yeah, so that's done. Are these different? Maybe. Okay, get the schematic. Place a program block with 4 outputs. We got that. Place a counter. Set its increment to 4. Counter. 8-bit counter. Okay. The increment has been set to 4. I guess plug it in. Boom. Place a... Okay. Add 6 registers, or custom components with registers. So we have registers here. So we need 6 of them. 5, 6. There we go. Click Edit Link Component on the Program component and connect registers 0 to 5. Connect the counter to 6 and the output to 7. Okay, let me just knock you out of the way. Link. Edit Link Component. So 0 is connected to 0. 1 is connected to 1. 2 is connected to 2. 3 is connected to 3. 4 is connected to 4. And 5 is connected to 5. 6 should point to the counter. And 7 should point to the output. Okay, it actually gives us... Okay. I'm gonna have to now connect all of these together. We might need to place more space between everything. Let me put this out of the way. Zoop. And then the input's down there. Okay. We might actually be using a lot of the same structure as Overture, honestly, but okay, let me put you further up. Wire spaghetti is what this level is called. Yeah, actually, we might want to section off it a little bit. Move this guy, move these guys down there, and this one there, this one there. Okay, and we want to probably add a bit more space between these components, just so we can have space to pass wire through. Maybe we basically leave like an entire length. There we go. So actually we could do it this way. Like that. And then we'll leave these at the bottom, which we can put them quite close by. Like this. Okay, next up. Wait, are these equally spaced? They don't feel equally spaced out. I think I might... Yeah, I want them to be kind of equally spaced out. Then we'll move you a little bit to the left. Okay, now we need to add opcodes. So let me just quickly load the idea of the schematic. So argument 1 and 2 are going via memory addresses, which is interesting. Is argument 1 and 2 Oh, argument 1 and 2 are memory addresses rather than raw data. Okay. Okay, I got it. So we basically don't need to worry about the top line yet. What we need is, wait, actually, don't we have fancier registers? Oh yeah, we do have fancier registers. I want to use fancy registers. Yeah, fancy registers. Okay. They still don't look evenly spaced out. Hang on. Actually, that is going to annoy me. Okay, now I know for a fact that they're evenly spaced out. And now we need to... There we go. Oh, am I miss? Oh, I lost a component in the way. On the way to perfection. Okay, there we go. Let's link these again. Okay. And now... So what we're basically doing is we're gonna be interpreting... Actually, are we using a 3-bit decoder for this? No, not a 3-bit decoder. Bit splitter. Is that the easiest way of doing it? Maybe it is. Basically associate... Do we have a constant machine? Oh, we do have a constant machine. Oh, that's very useful, actually. Okay, so we now have a constant value for 0. And we're just gonna... I guess we also should put constant values there, though I don't know if we'll need them. Oh, and we'll need a constant value there. Okay, so this will be set to 1. So we have a way of outputting the exact value that we need, which will be very useful. We need 4. This will be 5. This one is 6? I don't remember. I think this is 6. And this one's 7. Okay. Actually, we might have to put it at bottom. Ah, well, we'll figure it out later. And now we can use equality to control all the gates. So we'll have one... So the first line that we're building, we'll build a line. We probably need to connect it like this first. So the first line we're building is for argument 1. Where we need to... Okay, let's build the switches first. Wrong switches, delete switches. So, the first line we're building is for argument 1. Maybe we'll give it a bit more distance. Okay, like this. And then we'll run the line down. And we'll basically connect all of these components by this wire. There's a bunch of switch statements. Bonk, bonk, and bonk. Like this. But not. Oh, it's 6 but upside down. Okay, fair enough. And so now the way we check to see if we need to actually which one we need to trigger is we do an equality, and if true, that's when we turn this on. So we need to do, yeah, we'll do it like this. Okay. We need more equality. So we just test for equality. Oh gosh. Okay, there we go. We'll just put a bunch of these down to test for equality. And that way we can tell when we need to actually turn the switch on. All we need to do is just test the number that we want, and then when it's the correct switch, this will turn on. Oops. That. And then we'll connect like this. And so when the correct address comes in, we'll have the correct output. Wait, let me just double check something. I mean, we're basically doing that for the second one. I just need to double check if input and output have the same code, because we might have to do that as well. What? Input, output. Okay, wait, I actually even got the wrong numbers in. Input and output. Okay. 6. So this one is 7. This one's also 7. Okay. We're basically repeating this structure for the second line. As in, we're going to yeah, okay, we'll do it manually. So this is for argument 2. So let's build a giant line down. And add a bunch of equalities. Around there. 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 Then connect them with this. Oh, whoops, I'm connecting the wrong thing. I need to connect that thing. This thing. Oh, I see the problem. We've been connecting the wrong thing. That doesn't help. It'd be nice if we connected the right thing. Oh, we did connect the right thing last there. Just not here. Okay. here. And okay. There's one more here. Okay. That's good. Then all we need is to connect this value basically to this switch here. So it's setting it up again like this. I don't know how much of a distance we have here, but probably like this. And then we connect like this. It's about the same distance, I think. Doesn't matter. Then we just need to connect these ones like this. There we go. Maybe we'll hug it out. There we go. Oh, this is gonna totally become spaghetti. But so be it. Spaghetti is delicious anyways. Okay. We go here. We go here. We go here. Here, here, and there. Okay. Now we just add the switches. Okay, so we got argument 1, we got argument 2, so we can even branch them out now here. So argument 1 comes here. Argument 2 will be here. So this will be where we branch off, I guess, for calculation purposes. Now, we also need to connect inputs and outputs. Actually, we'll do input for the rest of these ones first. And basically, all we're doing is we're just doing the exact same thing. Except upside down. Can I just copy and paste? Maybe copy and pasting is easier. Hang on, I need to access the entire circuit. Copy and paste? Oh, actually, I don't think we can actually rotate it. Which sucks. Copy, paste. Oh, we can! Yeah. Okay. Upside down. Okay. But these switches we do have to turn around. So we'll have to connect them like this instead now. But otherwise, pretty much the same thing. Now we just have to output. And we run down like this. And then we just connect these ones in here, like that. Okay. And then we just need to connect this one. Ah, actually, we shouldn't be connecting it to switches. We should just be connecting this to the save button. Located right underneath it. That's the save button. Yes, that's the save. And then we just connect these directly in. Okay. No need fancy switch shenanigans. Just do it this way. Easy peasy. Okay. There we go. Okay, so these should work now for all the gates. And oh yeah, we need to, I guess, put inputs and outputs. Let me quickly do it for counter and for input output. So EIO. So this one is register 1. Yeah. I guess we put 2 switches. And wait, no, this is for output. This is for register 1 over there. Maybe only, let's use 1 constant. We know what the constant is for. This. Equality. So now what we do is we test. Maybe do one extra space like that. Probably need a lot more space actually, but. So this is for the first switch. So we've plugged this in here. We're actually going to turn. This boy is always going to be on. Oh, wait, that turns it off. Wait. I assume now it's connected. So that's for input 1. Let me connect this. Like this. And then we need to connect it to... Wait, no. This is input 1. Do you know where? I'm removing it immediately. We need to connect this to this circuit. Like this. There we go. Output 2. So this will go to output 2, which is here. And we're testing on which value? This one. Okay, and we connect these like this. Okay, so that's input configured. Now output. I guess we can always just swap these two around actually. Make my life simpler. Oh, but I just connected all these. Nah, screw it. No, yeah, let's clean it up a bit. We'll put output on the other side. That way we don't have to worry about crisscrossy wires. It makes more sense to do it this way. So. Yeah, the first one. First test we're doing is this one. I guess we could put it here, like this. Like that. And we connect it to here. And then the second one, we can put it here, I guess. And this will put a switch here, here, and then we can connect it to here. Okay, this looks much better now. And then the output is gonna be, so we want to test on this wire. So we put our test here. Like that. And we're gonna put I guess we want to disable it. Wait, does that mean we want a negation? Does that mean disabled? I don't... Wait, I don't... I can't tell. That's output, yeah. Why is it radiating values? It shouldn't be radiating anything. Huh. Let's just put a not here. Okay, and we need to connect this to the output, so let's just quickly let's do this. Alright, and one final thing we need to do. Counter. I guess we'll do the comparisons here. We'll just bring the counter value closer, and I guess the counter input will bring it closer. We'll actually just connect it directly. To this cable. So like this, and then the only thing we're testing, actually we can test this locally. Let's do all the tests locally, actually. We'll just have two wires going about. So, oops. Oh, come on, let me draw. So this one we're testing equality here. And this one will determine whether or not this turns on. The other two things we need is we need a switch statement here. Guess we'll just plonk it there on top for now. And a switch statement here. Connect this one here and that one there. This shouldn't be connected to anything yet. The first one will connect it to argument 1, which is here. There we go. The second will connect it to argument 2. Right there. Like that. And then we do the testing here. So we're testing for first argument here. So that will be the top one. This one right there. And that will trigger this one to go on. And then we'll test. We put this directly on top like this. Always good to minimize wires going about the place. Okay, we'll just need to fork this one over. And then we'll... There we go. Okay. I think all the registers are... All the registers have been connected properly. And now all we need to do is we just need to... Well, I mean, I guess we just need to do something with this, which is just going to be... For now, just add the two numbers and output it. Okay. Output is not enabled. Let me enable it. There we go. Short circuit. What is short circuiting? Oh, that's short circuiting. Okay. Output should be disabled. And this? Wait, register 2 should have a value of 14, not 16. Okay, let me tick through this. Okay, so 16, yeah. Now what do we have? We have 24, yeah. So why is it 16? Let's investigate. So this should be this should be 40. So right now 0 should be on. And oh, okay. Well, that would explain why. There are literally wires missing. There we go. Hey! Yeah, there's 3 more left. Considering I wasted like half of the stream on just like 2 very simplish problems. Let's just go the full way. Implement the following opcodes. The opcodes not ignores the second argument. Okay. So we just need to remove this bit now. So we have input, output, and this opcode will tell us what we need to do. You know, I just realized I could have actually done this as a component. Ask her. Should we do this as a component? Let's do it as a component. Switch schematics, new schematics, alu plus. Okay. We need an input. The input is an yeah, so that's the instruction. Instruction number 2. Okay, argument 1, argument 2. That's the idea. And then output. There. Okay. What do we need? Manual. Actually, let's let us, don't know what that does. Let us quickly read what we need to do. That's not what I want. I need, okay, add, subtract, and or not XOR. And or not XOR. Okay, I think I got it. This is overkill, but I don't care. Switch. Wait, no, we need the other switch. Yeah, we just need a few of these. Let me organize everything else first. So the first one is an add. The second one is a subtract. So that's just an add with a negation. We'll slightly stagger them. Like that. Make my life simpler. Oh, actually, no, we need to just stagger the switches. We don't need to stagger these ones. The next one is AND. The third one is OR. The fourth one is NOT. And the last one is XOR. And now we just need to connect all the bits. So we just need to do this. And do this. This. Like that. And now we just need to stagger the switches, so that we can pass wires through it. So something like this. And like that. Yeah, that's correct. Just connect all of these together. And now we connect these ones like this. And honestly, I have all the confidence that this will work, so I won't even test it. I'm just so confident that this will work. Okay, there we go. That's our component. Back. We just need to put our ALU plus. We just need to connect this component here. This component there, there, and there. We're done. Easy peasy. Next. Sometimes it is useful to load a value directly from the program instead of from registers. This is called loading an immediate value. In the leg architecture, we signal when we want to do this directly in the opcodes. We can do that in the following ways. When the 8th bit of the opcode is positive, use argument 1 as an immediate value instead of as a register address. When the 7th bit is an opcode, use argument 2 as an immediate value instead of as a registered address. Implement immediate values. Okay. So we need, I guess, yeah. Do we just... Oh yeah, just the opcode. Yeah. So... Oh, actually, we should probably do this there. Let me quickly do another component. Wait, no, we don't need to do another component. That's what molmix does. Silly me. Go back. We have a mux for a reason. I don't know why I call it a molmix, but yeah, this is what the component, this is what this component is for. So we can switch. And then so this is the normal value, unless, wait, is it? It selects input 1 on false, input 2 on true. Okay, so we actually want to connect this to input 1. Okay, and then we want to connect this thing. Oops. That's the opcode. So this, when the 8th input is, okay, 7th I think is this one, and then 8th is this one. Okay, so we got that unlocked. Let me actually bring it out by 1. Okay, there we go. And then we just need to connect the bottom ones to the registers. So that one connects to this. Wait. Connected the wrong one to this one. Or have I? No, that was correct. We want to connect this one to the bottom one here. And this one, we want to connect it to that one. Okay. Finally, add if statements to your circuit. For the if statement, the 2 arguments are compared, and if the condition is true, the counter is set to a jump address. The previous instruction had the 4 bytes represent opcode, argument 1, argument 2, result. For the if statements, the bytes represent opcode, argument 1, argument 2, jump address. In addition to the previous opcodes, add use unsigned less greater for the comparison. Each opcode does what their name implies. For example, the following jump to byte 16 is reg 0 if reg 0 is less than reg 1. Okay, this is definitely gonna be the hardest one. Okay. "32, 33, 34, 35, 36, 37. All of these have this bit. So this is the bit that we use to interpret what to do with this result. Normally, I guess we could do a switch. Normally, yeah, normally the bit goes this way. So we use a not to represent, normally we go this way. However, in the event of the number between being 32, we go the other way. And this just connects back to output, which is going to be, oh, that one. No, wait, actually. Scratch that. They'll set things correctly. We just need to do a little shenaniganry with how we deal with output. This thing. I think what we need to do, 8-bit constant, we do another mux. That one. We'll do the mux like this. We do another mux. We set the mux to 7. And so this will override whatever this is. Depending if 32 is on. So this will send, so if it's on, this will be 7 no matter what. And so this will read whatever the output is. Then we need to do another mux here. Oh, actually, hang on. We might have to wait, hang on. This is a very important. What happens if we don't send anything? Hang on. This is important. I guess what we need to also do is we need to interrupt this process. So like here. We need to do an AND. No. We need to somehow, maybe it is an AND, kind of. If this bit is on, then if this bit is on, we need both of these. We need another bit to be on as well. Oh, actually, if this bit is off, our bit is always going to be on. Let's put it that way. Yeah, let's do it this way. So we're doing an OR. I haven't decided how to do this yet, but don't worry. So either this bit is off, and then in which case, we're always going to allow, maybe we go upwards instead. We're always going to allow our jump to work. We are always going to allow the counter to update if it's off. Just, why can't I move my OR? Oh my goodness, I bugged. I bugged it. This is a... Oh no. Oh no. Oh no. What did I do? Okay, well, we're gonna have this random OR gate just chilling on the table. Hopefully when I reload the game, it will disappear. The ephemeral OR gate. Okay, so if this is on, if 32 is off, that means we'll always allow the bit to update. So we're doing this, and then we're gonna connect this via an AND. This. So this bit will only trigger if we allow it to trigger. And if 32 is off, we'll allow it to trigger. But only if... And if it's on, we will only allow it to trigger if this is true. Whatever true means. Mux. So this value is going to be the output of whatever this is, unless 32 is on, in which case it's going to be equal to result, which we'll have to grab now a link to. There we go. So now this is going to be equal to result. And now we need to figure out so I think what we need to do is LU plus is actually make us another output that we basically have to ignore. Yeah, we have to make another output, but then we have to ignore if our output isn't what we want. So let me just double check what we need to do. Yeah. So what we're gonna do is we're gonna make ALU plus. Let me... Okay, that's fine. Component factory, ALU plus. We're gonna make another output. There we go. Ooh, actually we can do that as well. Yeah, that could work as well. We use the output pin. Look, there's probably a cleaner way of doing it, but screw it. Yeah, let me move you here. Okay. This will always output whatever. I guess we can also make this output whatever, because we're disabling the pin whenever we're not interested in the result. With 32. So now, what do we need? Oh gosh, I need to remember. Equal, not equal, less, less equal, greater, greater equal. Okay. Use unsigned less greater for comparisons. Okay. Maybe we'll make it wider. Okay, we need to now grab both of these values. Like that. Okay, so now we need equal. We need not equal. So that's equal with a negation. Wait, we need the proper negation. There we go. Less than. So that would be... Oh gosh, we don't have a greater than. So we have to use this one. Less than. Less or equal. So we have to do this. Or equal. No, let's mix and match. We'll just have these three. No, we'll have these two, and then we'll mix and match. That's how we'll do it. I don't want to keep using the same components over and over again. Okay. So, and then we'll put them on at each switch. Switch. Actually, we might need to leave a little bit of space. Let's leave one switch's worth of space between each switch. So we'll need 6 of them. So 1, 2, 3, 5, 6, 7, 8, 9, 10, 11. Okay. Now, some of these will be easy. Actually, no. We need to do this. We need to do this as close as possible. So equal, not equal. We need less than. Less than or equal, so that's gonna be an OR. Greater than, so that's gonna be the negation of this. And greater than or equal. Wait, no. That's a NOR. It is the NOR of the ends and this. Greater than or equal is the negation of this. Okay. Now connect all of them together. Like this, and then we connect this here. And then we need to also then connect all of these, but we can just use the same decoder. Okay. There we go. And so that's that. Oh no. There we go. Wait, I think we need to connect this to this thing. Okay. And I think that's good. I think we've done it. We've connected all the components. I probably forgot something. Okay, so now it should connect properly, assuming the inputs are correct. So let's check Elu Plus first for potential mistakes. Elu on 32. So when this bit is on, this should turn on. And so whatever the input is, so 1. Okay. So it just has 1, 2, 3, 4, 5, 6. And then everything should be off. Okay. This should work. Okay. So next. Output, output should be disabled. Is output not disabled? Oh, because I put the wrong code in. It should be 6. Okay, there we go. Okay. Not a mistake. Next tick counter will be 20, but it should be 24. So this is not updating because this is set to 24. Okay. That makes sense, because I grabbed it from there instead. So I should grab it from here. Yeah, I grabbed it too early. This should work. Oop. It's still 24. Now, why is that the case? Oh, because I'm still grabbing it from the wrong place. I need to grab it from here. Okay, now I'm grabbing it from the right place. There we go. Congratulations, you finished the leg computer. I will show you some upgrades you can make on the path to implementing function calls, but from here on the details are up to you. I won't tell you what opcodes to use and so on. Yay, we did it! 2 hours and 42 minutes stream, woo! On not that many chapters. Yeah. Admittedly, half of it, like a full hour, was spent on these two. Unsigned and XOR. For no reason. But yeah, so when I actually edit this down, I'll probably end up having to add additional timestamps to make sure people can skip to the right areas if they're just interested in the solutions. But anyways, thank you very much for joining me. I'm gonna end things here. So hopefully you enjoy this VOD, stream, whatever. And I hope you have a good day. Goodbye.